Good morning. We are going to get into hypothesis test number 2, which is the situation where mu is known and sigma is unknown. Mu is known, sigma is unknown. What we're going to be doing is very, very, very similar to what we had been doing the last couple sessions. We have the same research question. Is there a significant difference between the population mean and the sample mean? Is there a significant difference between the population mean and the sample mean? And the fact of the matter is that we rarely know sigma. We rarely know the population standard deviation. But we do know S. S is very easy to obtain. Sample standard deviation is very easy to obtain. So we use S to estimate sigma. As in, our point estimation. Where before we were working in a distribution of Z, we now are working in a new sampling distribution of the mean called the T distribution. The T distribution. So we have a distribution of T. And remember, class, that this is a sampling distribution of the mean. It's a sampling distribution of the mean. We have an infinite amount of sample means on this theoretical sampling distribution that's put forth in the central limit theorem. So we have all these little means. We have some with not a whole lot of sampling error, some with quite a bit of sampling error. The T distribution and the Z distribution are very similar. It's kind of like the difference between a Ford and a Chevy. They're really similar. But we have this statistical concept that's brand new. It's called degrees of freedom. And we're going to symbolize it using a DF, degrees of freedom. Now there's an explanation in the book, but it might confuse you a little bit. What I would like you to just think of is that degrees of freedom relates to sample size. It's very similar to N. So it relates to sample size. It's something very similar to N. If we were to write df equals N, that would imply that df and N are the same thing, right? Just think of df equals N minus 1. Something pretty similar to N, but degrees of freedom, something really similar to sample size. And like I said, there's a little bit more sophisticated explanation in your book. But for the purposes of this class, let's just stick with that. The DF and N are pretty similar. We have this statistical hypothesis test that helps us answer this question. It's called a one-sample t-test. It's in Chapter 9. Our t-statistic is the sampling error numerator divided by the standard error of the mean, you see a lot of similarity between this and z, the z-test, except that this denominator is a little bit different because s is given, right? We're just using a different form of this standard error of the mean. And that standard error of the mean is just simply the standard deviation of all these little infinite amount of sample means around mu. It's equal to s over the square root of n. Let's see how this all works in a series of examples. And again, class, you're going to see a lot of similarity between what we're doing today and what we have been doing in the last couple of class sessions using the z-test. Let's take a look at our handout. Example number 1. The Smith Anxiety Measure is a psychometric instrument designed to assess levels of anxiety in elementary school-age children. The mean anxiety score on the SAM for the general population of elementary school children nationwide is 14.55. We have a national average here that they're calling mu, population mean. We randomly selected a sample of 31 children from an elementary school in Port St. Lucie and administered to them the SAM. Their mean score was 11, with a standard deviation of 6.085. Do these children show significantly lower levels of anxiety than do children from the general population? Same kind of research question. I really don't know. What I can see here, though, is about a 3.55 difference between the sample mean and the population mean. Now the question becomes, is this difference, enough to be considered significantly different from mu? Where does this sample mean fall on the sampling distribution? If it falls out in the tails, what's my decision going to be based on the null, class? If it falls somewhere in the middle, what's my decision going to be based on the null? Accept. Right. This, again, is the first set of information. When you're doing these problems, this is how you should set them up. So when you're doing homework problems in the book, this is how you should set them up. Extract the information, list it. We proceed to step 2. We write the null hypothesis, H sub 0 colon mu equals 14.55. Alternative hypothesis, H sub 1 colon mu is not equal to 14.55. Now again, we see a classic two-tailed null and alternative situation. We only run two-tailed tests in this class. Equal sign, not equal sign, period. This thing calls for an O5 alpha. So the likelihood that if I do reject the null, that I make an incorrect decision is about 5%. Notice that's that small potential error in statistical decision making. And we're running a two-tailed test. And they actually chose a two-tailed test because before they actually gathered these 31 subjects, they didn't know whether this sample mean would be below mu or above mu. Turned out to be below, that's fine. They picked a two-tailed test just to be safe. And again, we know that before we run any statistical test, a p equals alpha. It's going to change after we actually compute t. P is either going to be less than alpha, in which case we would do what? Reject, right. If p is greater than alpha, what do we do? Very good. Degrees of freedom is n minus 1. 31 minus 1 is 30. We can find a critical value. This gets a little bit different. Get your textbooks out, please. go, in the 6th and 7th edition, go to the front cover. Go to the back cover. In the 8th edition, go to the back of the book.
In the 6th edition, it's back to the 2
6th and 7th edition, back cover. 8th edition, table 5 on page C21. In the 8th edition, table 5 on page C21. Everybody get there? In the 6th edition, back cover. Back cover. There we go. What we have in front of us here, class, is a table of T critical values. Now you see lots of numbers here. This is a little bit different than the Z table, okay? Up in the upper right-hand corner of the page, you see the area. This is actually the area in the right tail. This is considered a one-tailed set of T critical values. That's just the way this textbook does it. I didn't select the textbook. It's considered a one-tailed set of T critical values. And because this is so, and we're running a two-tailed test, we actually have to divide alpha by 2 to get the area in the one tail, which we know to be 2.5%, right? 0.025. We go across the top to 0.25. We go across the top to 0.25 and down the side to 30. And we have a number there. And what is that number?
2.042.
2.042, positive or negative. Again, we're dividing alpha by 2 because this table is a one-tailed set of critical values. We're running a two-tailed test. We divide alpha by 2 to get the area in the one tail, which we know to be 2.5%. We go across the top to 0.25. And in this case, down the side to 30 degrees of freedom. We match them up. In this case, we get a number 2.042, positive and negative. This is telling us, class, that at 30 degrees of freedom, about 95% of the area under our sampling distribution falls within this interval. So we're out of the world of 196, as we see. This is the difference between the T sampling distribution and the Z sampling distribution of the mean. I will tell you that as sample size increases, the T distribution and the Z distribution are identical. They become identical. Regardless, if T exceeds one of these values in either this direction or this direction, we have enough evidence to reject the null. We have our second set of information. On the exam, you're going to be finding lots of critical values, lots of T critical values. Do not forget, we're running two-tailed tests. Always divide alpha by 2, area in the one tail. If alpha was 0.1 and we divided by 2, this number would be 0.005. Well, it's not in this case. Across the top to this, down the side to DF, match them up, you got your critical value. We have a population mean of 14.55. Let's compute T with a special emphasis on what's going on, of course, with our standard error of the mean. It's going to tell us a lot as to where this sample mean is going to fall. It's going to fall somewhere over here, I think. X bar 11 minus mu 14.55 over the standard error of the mean. S 6.085 over the square root of 31. Square root of 31 is 5.57. Standard error 1.092. So class, in terms of t units in this case, what does 1 t unit equal to? 1.092. This answer should come immediately. If it's not, you're just not doing anything, all right? And the test is going to come, you're going to take it, you're going to be all stressed out, and then you're going to get a bad grade, and then you're going to cry, all right? So don't cry. There's no crying in statistics. Didn't they make a movie about that? With Tom Hanks? No. That was a great movie. 1 t unit equals 1.092. So we'll just do what we do. Somebody help me with their calculator. 14.55 minus 1.092?
13.458.
Minus 1.092?
12.366.
Minus 1.092?
11.274.
Great. That sample mean of 11. I'm talking loud because I want the voice to come over because it's the voice on the YouTube is a little bit light, so I'm going to scream. Where does that 11 fall on the sampling distribution? Well, here's 11.274. Where does that 11 fall? You know what? I bet you it's about right here. That data point, that X bar data point 11 is about right here. It's going to correspond to a t about right there. What do you think our decision is going to be based on the null, class? You bet your bottom dollar. Let's do it formally. Negative 3.55 divided by 1.092 gives us a t of negative 3.25. And now we formally make the decision using that critical value approach in the book. It's also the rule. We compare the calculated test statistic to the critical value. We see it exceeds it, in this case, in the negative direction, right? Therefore, our decision based on the null is to reject the null. Yeah. Yep. Before we actually ran the t-test, our needles were right here at the critical values. But t turned into negative 3.25. This one stayed right here, it didn't move. This one shifted from here over to negative 3.25. It made this area of p way smaller, therefore having a total effect on p of making it less than alpha, less than 5% of the area under the sampling distribution of the mean. If p is less than alpha, reject the null. And again, class, what's going on here? Well, we've determined, based on this hypothesis test, that this event, which corresponds to now this event, this is the raw score, this is the standard score, right? We've deemed these events rare. Rare. Rare events are significant events. What we're saying is that, means of this magnitude don't happen every day. T's of this negative magnitude, they're pretty rare events. Rare events are significant events. Yes?
Would it be p is less than 0.05 or 0.025 divided by 2?
Very good question. Alpha still, I'm so glad you asked that. Alpha is still 0.05. We simply do this procedure to find the critical value. But alpha is not 0.025. No. Alpha is still 0.05. We simply do this because this is a one-tailed set of critical values. So in order to find the correct critical value, we need to divide alpha by 2 to get the area in the one tail, which this is putting forth here in the text. Go across the top to 0.25, down the side to DF, find the critical value, and so on and so forth. Let's answer the question. Class, do these children show significantly lower levels of anxiety than do children from the general population? Yeah, apparently so. Now again, we haven't proven anything. All we're doing is providing statistical evidence that suggests that this sample of 31 students have significantly less anxiety than the norm, than the national average. Now again, you know, there's a small chance that my decision to reject this null was not a correct one. You know, so I rejected with about 95% certainty. What's the status of type 2 error, class? What's the status? Right, it's irrelevant. It's irrelevant. Okay, let's do another one. Hurricane Andrew. Does anybody remember Hurricane Andrew? Yeah. Was that a significant event?
Yes.
Yeah, it was. Cat 5 hurricane. Hurricane Andrew swept through southern Florida, causing billions of dollars in damage. Because of the severity of the storm and the type of residential construction used in this semi-tropical area, there was some concern that the average claim size would be greater than the historical average hurricane claim of $24,000. We have a historical average here, $24,000. Several insurance companies collaborated in a data experiment. They randomly selected 84 homes and sent adjusters to settle the claims. In the sample of 84 homes, the average claim was $27,000 with a standard deviation of $2,400. Is there overwhelming evidence that the average home damage is significantly greater than the historical average? I don't know. What I do know here, class, is that we have about a $3,000 difference between the national average and the average of, the mean of this sample of 84 homes, which were probably randomly selected in the Homestead area, right? Or whatever. We have a population mean of 24,000. It goes right in the middle here. We'll set the null hypothesis. H sub 0 mu equals 24,000. H sub 1 colon mu is not equal to 24,000. Again, classic two-tailed null and alternative. This thing calls for an O5 alpha and a two-tailed test. We know that before we run any statistical test, P equals alpha. Degrees of freedom is n minus 1. 84 minus 1 is 83. We can find a critical value. And again, because this t-table is a one-tailed set of t-critical values, we have to divide alpha by 2 to get the area in the one tail, which in this case is 2.5%. We go across the top to 0.25, down the side to 83.
It's not on the table.
Oh, it's not on the table?
No.
My table goes to 7.5.
Is that right?
Yes, sir.
Yeah.
So let's just go down to infinity. What's that number?
1.960.
I'll be doggone, 1.96. Yeah, we're back in 1.96 land again. And this is the similarity between the t-distribution and the z-distribution. As sample size increases, z and t become pretty identical. So for now, our critical values are the 196s. We have a population mean of 24,000. Let's compute t with special emphasis on the standard error of the mean. See what's going on over here in terms of where this individual sample mean falls. X bar minus mu, 24,000, over the standard error of the mean. S, 2,400, over the square root of our sample size, 84. 2,400, square root of 84 is 9.17. Standard error of the mean, 261.70. Our unit of measurement is dollars, right? 1 T unit in this case on the sampling distribution is $261.70. So we do what we do, 24,000 plus 261.70, 24,261.70. And somebody help me here. And one more time. All right. Now things get a little bit clearer, don't they? Because now we look, the X bar of 27,000, where does that fall on the sampling distribution relative to everything else? Oh my gosh, here's 2470. That 27,000 is like way over here. Was Hurricane Andrew a significant event? Well, yeah, I mean, now we're seeing, you know, some of the... What do you think our decision is going to be based on the null?
Rejected.
Let's formally do that now. 3,000 divided by 261.70 gives us a t of 11.46. Wow, that's a big one. Pretty rare event. Rare events are significant events. Let's use the rule. We compare the calculated statistic to the critical value. We see it exceeds it in the positive direction. Therefore, our decision is to reject the null. Yeah. And on that right side, that needle shifted from positive 196 all the way over to 11.46. On the left side, the needle stayed right there. On the right side, we had a big shift. What was its, you know, what happened to the P region in this case? It got smaller than alpha. If P is less than alpha, we reject the null. So class, question. Again, the whole purpose of this is to help answer a question. In this case, is there overwhelming evidence that the average home damage is significantly greater than the historical average? Yes. Yeah, absolutely. And if you want to ask the question why, this is why. This T, which corresponds to this sample mean of 27,000, remember this is the raw score, this is the standard score. We're just converting, are considered very rare events. Rare events are significant events. This stuff doesn't happen every day. Statistical significance, a statistically significant difference. Now again, you know, there's a small chance that I may have been incorrect in my decision, about a 5% chance that my decision to reject the null was not a correct one, about a 95% chance that my decision, you know, is a correct one. The status of beta is what? Right, it's irrelevant. It's kind of a non-issue. If you don't know what beta is, you're in trouble. I'm assuming now that you know all this basic stuff that we've been going over, all, you know, all that you know it now. You better know it by Thursday. Okay, let's try it again. Overton University claims, it's a claim, it's a statement, it's a hypothesis, that because of its superior facilities and close faculty supervision, its students complete the PhD program earlier than usual. They base this assertion on the fact that the national mean age for completion of the PhD is 32.11 years old. Whereas Overton's mean age of their 26 PhDs is 29.61 years old, with a standard deviation of 6. Test the validity of their assumption. They're basically, they're claiming that because of their superior facilities and close faculty supervision, that their PhDs actually graduate with the PhD at a significantly lower age than the norm. Okay, they're basically just kind of, tooting their horn here. They want us to test the validity. Is this assumption accurate? I don't know. We have about a 2.5-year difference between this and this. Our job now is to determine, is that difference significantly different? We have a mu of 32.11. On the exam, you will do 2 z-tests, 2 one-sample t's with questions associated, and lots of other questions. Lots of other questions as well. So if you see a scenario like this, and I ask you to write the null and the alternative, this is what you do. H sub 0 colon mu equals 32.11. H sub 1, mu is not equal to 32.11. This problem calls for an O5 alpha and a two-tailed test. Okay, help her with her stuff after class, please. Before we run any statistical test, P equals alpha. Degrees of freedom is n minus 1. 26 minus 1 is 25. We can find a critical value. We're running a two-tailed test. On the exam, you're going to do a lot of this. You're going to find a lot of critical values. It's really important. Because this table is one-tailed, and we're running a two-tailed test, we have to divide alpha by 2. 0.5 by 2 is 0.025. Go across the top to 0.25, down the side to 25, and there's a number there.
2.060.
2.060. Negative 2.060. Positive 2.060. If t exceeds this in either direction, we have enough evidence to reject the null. We have phase 2. Next step, let's compute t with special emphasis on, what's going on with the standard error of the mean. 29.61 minus 32.11 over the standard error of the mean. S is 6 divided by the square root of 26. Square root of 26 is 5.1. Standard error of the mean, 1.18. 1.18 years. Class, is t going to be positive or negative? It's going to be negative, yeah. We're going to work on this left side of the distribution. 32.11 minus 1.18?
30.31.
Minus 1.18? What's that?
Yeah, I messed up on the first one.
The first one is 30.9.
Sorry.
Minus 1.18?
29.75.
Minus 1.18?
28.57.
Great. That sample mean of 29.61, where is it going to fall? It's right about here. Let's see if we reject the null. It's going to be pretty close. 1.18. That looks like negative 2.5 divided by 1.18 gives us a t of negative 2.12. It looks like we're going to reject. We compare the calculated statistic to the critical value. We see it exceeds it in the negative direction, right? Therefore, our decision is to do what? Yeah, reject the null. What happened to p? Yep, it got smaller. And, just to quiz you a little bit, class, if t would have been, negative 1.5, what would my decision have been? Accept the null. What would have happened to p in that case? It would be greater than alpha, yeah. If our t would have been positive 1.68, what would my decision have been? Yeah, accept the null. What would the status of p be, again? It would be greater than alpha, yeah. Non-rejection region, rejection region. Let's look at the question. Test the validity of their assumption. They're claiming that their students complete the PhD program in significantly shorter time than the norm. Is that assumption valid? Yeah. Yeah. Apparently so. We have statistical significance here, but not a whole lot of practical significance. I haven't talked about practical significance. There's about a 2.5-year difference here. What's the difference between being 29.5 years old and 32 years old? Not much. Not much. So we have a statistically significant difference, but not a whole lot of practical significance. Okay, the one sample t-test. So you guys see a lot of similarity here. I'd like to change gears a little bit and talk about something really important. And it's actually the reason why we reject the null or accept the null. This topic, this statistical topic, is actually the reason why we have significance or we don't. So in every hypothesis test that we do, whether we reject or accept, there's a reason for it. We call that reason statistical power. Just symbolically, we represent power 1 minus beta. Statistical power is thought of as the likelihood of correctly rejecting a false null. It's the likelihood of correctly rejecting a false null. The likelihood of correctly rejecting a false null. Now there's some tables in your textbook that I want you to become very familiar with. We'll actually go over that on Tuesday. Another way of thinking of this, it's actually a simpler way, it's the likelihood of finding significance. It's the likelihood of finding significance. And power, statistical power, is a function of four things. Power is a function of four things working together to produce a statistic that's either significant or not. The first element of statistical power we call mean difference. Mean difference, just simply this mean difference. As mean difference increases, power increases. As mean difference increases, the likelihood of finding significance increases. What do we mean by this? Well, just look at the numerator. This is the mean difference. Class, if this mean difference gets really, really, really large, what's its effect going to be on, everything else being equal? If this mean difference gets really, really, really large, this numerator, what's its effect going to be on t? It's going to make t really large. And if we have really large t's, aren't we going to reject a lot of nulls? Yeah. Yeah. As mean difference increases, power increases. Our second element of statistical power is just good old sample size. Good old n. As n increases, power increases. As n increases, power increases. Let's look at this mathematically again. Real simple. Here's n. It's a part of the denominator. See that? As this n gets really, 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 really big, as this denominator in the standard error of the mean gets really, really, really big, what's its effect on this denominator? It makes the denominator really, really what? Small, right. This is 6th grade math here. And if this denominator gets really, really small, what's its effect going to be on t? It's going to make it really big. If we have really big t's, aren't we going to reject a lot of nulls? Yeah. Yeah. As n increases, power increases. Our third element of statistical power is actually a new term that we'll be using later in the course. It's called within-group variability. And we'll just abbreviate it WGV. Within-group variability. And that's actually the variability within group. What is the measure of variability in this formula? Oh, it's the denominator. Variability, dispersion. This is actually, these are dispersion estimates. S and S sub x bar, dispersion estimates. So class, as WGV decreases, as within group variability decreases, power increases. What do I mean by that? Well, again, if this denominator gets really, really, really small, what happens to t? It gets really, really large. If we have really large t's, aren't we going to reject a lot of nulls? Yeah. And finally, our fourth element of power is just good old alpha. That likelihood that I've committed a type 1 error. And we can say as alpha increases, power increases. What do I mean by this? Well, let's readdress alpha. You remember I said common alpha levels 0.1 or 0.05 or 0.01 or 0.001. And we now know that this is the most common. But if you notice, the numbers are increasing this way. So, you know, this is a larger number than this is, right? You know, this is a larger number than this is. 0.5 is a larger number than 0.1. So class, tell me, where is it easier to reject the null? 0.5 or 0.1? 0.5. Why? Because the critical values are lower. Think back to the z-test. What were the critical values here for 0.5 two-tailed? 1.96. What were the critical values here for 0.1 two-tailed? 2.58. So where is it easier to reject the null? Here. 0.5 is considered a more powerful alpha than 0.1. Why? Because the likelihood of finding significance is increased. It's easier to reject the null. Now, this is considered more strict. It's considered more conservative. It takes a higher test statistic to reject here. But this is still considered more powerful. Okay. The reason why we either have significance or we don't. Power. And if we don't have significance, you'll hear a lot of people saying, well, the reason why we don't have significance is because we don't have enough power. What they mean is we don't have enough of, you know, one of these things that actually produces a significant statistic. So in every single case, from now, of course, actually when we started the z-test until the end of the semester in April, you know, in every hypothesis test we do, this is always an issue. Power is the reason why we either reject or we accept. And it's just simply a function of these four things. So in any formula that we're working with, and we'll be working with a lot of them, this is actually the easy stuff. This is real, we break our teeth with all this. This is real simple stuff. It's going to get way different as time goes on after the test. And then it's going to get way more different after exam 3. But again, this is all, pretty standard, reason behind why we reject or accept. Okay, I would encourage you to really study the basics. That first lecture notes sheet, that all those little pieces and parts, and then start working some of these problems. Tuesday, we're going to continue this section and then have a bit of a review. And that concludes today's lecture, and I will see you guys next time.